You could argue that all the experiments are simply wrong, but this is highly unlikely. Sudbury Neutrino Observatory web page. Right. The solar neutrino puzzle. Despite the mystery and the importance of the Higgs particle to the standard model, my favorite is still the neutrino. Far and away, it's the most intriguing and appealing of all the fundamental particles to me. I'm not quite sure why. It's a property that is such a mysterious little object, and even today, there are still lots of aspects of neutrino that we don't really understand fully. The standard model is a minimal theory. That is to say, we take what data we have and we write down the simplest possible model that's consistent with it, and then we go out and test and see how well we've done. So far, it's worked very well, but just recently there have been some hints that perhaps we haven't quite got the story completely correct with the neutrinos. So today, I want to talk about where we are at and what we are learning about neutrinos. Remember, what these particles are. This is a particle which is fundamental. It's one of the leptons. It has no mass, no charge, no color, and no strong force. The only force of nature that it can feel really is electro weak. Truly the weak force of nature. Not the electric part, just the weak part. The massless business is a part of the mystery of the neutrino. What does it mean for a particle to be without mass, massless? It's incredibly easy to produce. The other massive particles we are most familiar with, it's the photon. If you take a photon, it's a traveling electromagnetic energy bundle, but it has no rest mass. You can't take a photon and make it sit still. It's always running at the speed of light. A neutrino is quite different from a photon. It's not a force carrier. It is itself one of the fundamental constituents. Yet, what we're saying is you can't take a neutrino and hold it still. If it's massless, relatively say it's always going to travel at the speed of light. Now, a deep question that you could ask is, why is it massless? See, that's a little bit of a funny question. In the standard model, don't we just collect the masses and write them down? We fill out tables by looking at the data, so the answer is, it's massless because it appears in experiments to be massless. But sometimes in a standard model, there is a reason. For example, there is a deep theoretical reason why the photon is massless, namely gauge symmetry. Gauge symmetry is a principle. It's the symmetry of the universe. It has to do with the nature of electricity and magnetism, and if gauge symmetry is correct, then the photon must be massless. It works out from the mathematics. It shouldn't necessarily be obvious to the casual viewer, but it is a definite consequence, and there is no such a principle associated with the neutrino. There is no fundamental or deep mathematical reason why it needs to be massless. We have just said that it is because, so far, there is no experimental evidence for sluggishness or inertia associated with the neutrino. Alright. As long as there is sluggishness or inertia, it implies there is no mass, because everything that has mass has an inertia in the form of the gravitational field. So yeah. So if there is no inertia, no sluggishness, there is no mass at all. It's a deductive way to figure out what will be there. So it's pretty much frameworking with it. Suppose we made a very delicate little experiment and measures the mass of the neutrino, and it turns out not to be the zoo after all. Maybe it's a 0.00001 in some unit system, a tiny but non-zero number. Would that break the standard model? The answer is definitely not. You could just scratch out the zero in the table and replace it with 0.00001. Actually, you'd have to do a little bit more than that. The standard model, as it's constructed, really makes a neutrino special. There are certain characteristics of the neutrino. For example, the fact that every neutrino in the universe has, as it's running away from you, has a spin that points counterclockwise. It's a left-handed particle that would also have to be modified. That statement about the world would get fixed up if we discovered that neutrino has mass. Right. People have been looking for many years, making very delicate measurements of the production and detection of the neutrinos, trying to see if they have some mass. We have no direct evidence yet, so whatever it is, it's a very small number. But we do have some hints now that maybe it isn't zero. Wow. There is another aspect of the neutrinos that's very important in our present understanding of them. There seems to be 3 different kinds. We call them flavors of the neutrinos. Yes, flavors. What's next? It's just a kind of a whimsical name. There are electron flavor, the muon flavor, and the tau flavor. Yes, that seems to be distinct particles. In fact, now we talk about electron numbers as a property of particles. As an electron or an electron neutrino, each has electron number 1, so electron number apparently is a conserved quantum number in nature. As particles move and interact, an electron could just bounce, preserving an electron number, or it might undergo a weak interaction. So a little double boson might be exchanged and particles transform. The electron will transform, but only into an electron-type neutrino, in order to conserve total electron number. Yes, there is always conservation law, being symmetry, right? Yes. Again, until recently, it was believed that electron number and separately muon number and separately tau number were absolute exact conserved numbers. You know, Emmy Noether, a mathematician in the early 1900s, said that when you have a symmetry of nature, it's associated with the conservation law. We don't have any symmetry of nature that we've discovered that would correspond to the conserving electron number. So, it's sort of the accidentally conserved things. When that happens in the nature, you are sort of looking and asking if we can find an experiment where we see lepton number changing. Again, this is something we are hunting for, and I'm going to tell you about the way that we hunt for these things shortly. Right. Let me leave the world of neutrinos for a moment and tell you about the sun. The sun, helio. It seems disconnected, but we'll see there is a very close connection. For many years, physicists and astronomers have been trying to understand what the sun is, and how it works. It is obviously very important for an astronomer to know what the sun is, because, after all the other stars are suns as well, and this is the closest one, right? We can study it very easily, so people have constructed what you might call the standard model of the sun. I use the word standard now in a completely generic English sense, just as an ordinary, everyday model of the sun that people can accept and believe that describes how it behaves. How bright it is, the color, what it's made of, and all of the things that you associate with the sun. This truly is a model. It's not a fundamental theory of nature. We just have a big ball of gas, and we are trying to describe it as accurately as we can. There are certain things about the sun that are very difficult to measure, such as how hot it is in the middle. We can't get in there with a thermometer, so we have to make deductions. Yes, deductions! Like mathematics. based on what you see on the outside, based on the laws of physics and nuclear physics as we know them, what should the temperature be in the middle? So the standard model is a kind of the collection of all the branches of the physics, heat and thermodynamics and light and sound and vibrations and materials, all put together to describe this object, and it's a very successful model. It can predict all of the features of the sun down to the details such as sunspots and solar flares. To a certain extent, we have a good understanding of the sun. Yes! This is how science works, right? One of the aspects of that understanding is a nuclear reaction at the core, which powers it. We know how bright it is, so we know how many such nuclear reactions are occurring very, very precisely. Wow, so mathematics, isn't it? Yes. We know what they are. It involves protons smashing together with other protons at very, very high temperature and energy, forming nuclei. It's a strong interaction of the nature that binds protons and neutrons together. Yes. Here, you've got protons binding to protons, and in order to stabilize, one of the protons has to turn into a neutron, effectively. Yes. And that is a transformation, that's weak decay, and so neutrino is released. According to the laws of the nuclear physics, if you know how many nuclear reactions are going on, you know exactly how many neutrinos are coming out of the sun. Yes! Wow! So the standard solar model makes a very definite prediction for how many neutrinos flow out of the sun every second. And since we know how far away we are, how many are passing through us, our bodies, our detectors, this is arithmetic, right? As simple as it is. A long time ago, in the 1960s, a physicist named Deley Davis decided this is a big number. It is, to be exact, 60 billion neutrinos per square centimeter per second everywhere, and here at the orbit of the planet Earth, almost 100 billion. Whoa! That's a big number. Even though these neutrinos are very low energy, they are coming from low energy nuclear reactions in the sun, and even though neutrinos are very wimpy particles, if we build a big enough detector, thought Deley Davis, we should be able to find the evidence that there really are these neutrinos coming from the sun. Wow, so savvy, isn't it? After all, any individual's neutrino has a tiny probability of interactions, but you've got an awful lot of them. So you are buying a lot of lottery tickets, and if you could build a big detector, you would just be increasing the number of nuclei available for those little neutrinos to bump into. Wow! So what are you going to do? Deley Davis looks at all the various nuclear reactions where the neutrino comes in. He hits a nucleus and makes a transformation occur. And his favorite was to take a chlorine atom, wow, Cl, and if a neutrino hits it, the neutrino will convert into an electron because it's a weak interaction, and the chlorine nucleus will convert into an argon nucleus. Wow! That's what's known from the nuclear physics. Argon is a gas, but it's not only a gas. This argon that you produce is a radioactive gas, so it should be fairly easy to detect. Yes. A little Geiger counter would click if an argon atom was nearby and decayed. Wow, so classic. So what we need is a big tank filled with chlorine. Yes, so cheap, so efficient, so budget. Yes, so simple. Wow. What he used was cleaning fluid. Wow, cleaning fluid? It's the cheapest fluid on earth except water, you know. When you go to the convenience store, chlorine fluid is sold around $1, €1. It's so cheap. Cheaper than any soft drinks over there. A very clever idea because it was carbon tetrachloride, so it has lots of chlorine atoms in it. It's also quite innocuous stuff, not big biohazard. Right. He took a railroad car, a tanker, and filled it with a carbon tetrachloride, then buried it deep in the mine, the Homestake mine in South Dakota. Haha. It was buried in a mine because we are looking for very, very tiny signal. Only once or twice a day is such an event likely to happen, according to the laws of particle physics, which he knew about in the 1960s when he built this device. If we put this detector here in the room, remember there are cosmic rays raining down on us all the time, and cosmic rays can also make a nuclear reaction happen, and at a much higher rate because the cosmic rays interact electrically as well as weakly. And strongly as well as weakly, we would just be completely swamped out with other stuff going on. Yes, it's noise, right? It's as if you are looking for a really dim light and you are not going to go into the bright room and look for the light. You are going to go into the darkest room you can possibly find. So they went deep down into the Homestake mine in South Dakota and wow, just started waiting. So savvy, so cheap, so classical, so simple. The idea was that every now and again, a couple of events a decay, a single atom. I mean, you have to realize the spectacular scale of this experiment. Or one or two atoms in this railroad car is going to transform from the chlorine into argon. Ha ha ha. Argon is a gas, so it will bubble up to the top, and you have some collectors up at the top, and then you hold them in front of the Geiger counter for a while to see if a radioactive argon atom will appear. He would sweep through the tank with some other gas to collect the individual argons, and it worked. Yes, it was an amazing experiment, and indeed, every month he would collect a couple of dozens atoms. Wow. Good job, Davis. Now, remember, Deley Davis knows what the prediction is for the total number of neutrinos, and he knows all of the nuclear and particle physics of the day, which is pretty much the same as what we know today, almost, so he could make a quantitative prediction. The standard solar model combined with the standard model of the particle physics says you should get so many neutrino events per month. What he got was about a third of that. Just a third? At first, people were just very proud of him. He did a great job, which was, in a certain sense, the first direct proof that neutrinos comes from the sun. You might even argue it's the first direct proof that the sun is really undergoing nuclear reactions. Yes. This was very cool, good stuff. But after a while, this factor of 3 started to bug some people. They wanted to know why they were seeing fewer neutrinos by a big factor coming from the sun than were predicted. Right. At first, it was known in the literature and began to sort of grow and be called the solar neutrino puzzle. Solar neutrino puzzle, ha ha ha. So where are these solar neutrinos? I think that even when I was a graduate student, I remember reading about the solar neutrino puzzles, and most people said, come on, maybe he is, missing a couple. I mean, these are atoms in a giant tank. Maybe he doesn't collect them all, but he was a great physicist. Actually, still is. He's continuing work on this experiment, and really? He did a lot of careful checks. For example, he would take a highly radioactive source and put it right next to his tank. He had a source and he knew how many neutrinos were coming out of it. And then he did collect what he expected. Wow, that proves that he was capable to collect all of the amount of things that he aimed. So there is no doubt that he collected all of the stuff out of his experiment. So there is no possibility, there is only few possibility that he missed something. So there really did seem to be something special about the neutrinos from the sun. He really seems to understand his tank, right? This kept going. He was collecting more and more data and improving the accuracy. Finally, other people began to get interested. There were several new experiments in the year after this. In the 1980s, the United States got together with the Soviets and built something kind of like it down deep in the mine, but instead of using chlorine, we used gallium, which is a big tank of liquid metal. The gallium would transform. The neutrinos would turn into the electrons and gallium would turn into germanium. Then we could count and collect the germanium, right? There was a European experiment also that was done with the same idea with the gallium. Both of those independent experiments agreed that the number of neutrinos coming from the sun is fewer by a factor of 2 in their case, or 3 in the chlorine case. Wow, than what we expected. So the solar neutrino puzzle is just getting bigger. It's not going away. Haha. The Japanese entered the story with a giant water detector, a giant tank of very, very pure water. It was called Kamiokande, deep in a mine in Japan. And again, it was a neutrino coming in, walking into the water and making a transformation. But this time, you have something extra. When the neutrino walk into the nucleus, or the electrons, in the water tank and transformation occurs, some energy was dumped. And that energy carried the momentum of the neutrino. If the neutrino came in from the certain direction, you had a little spray of the particles going out in that directions. If the tanks are lined with the detectors, actually just light detectors, big photomultiplier tubes is a name for a big light detector, right? It was possible actually to see which direction the neutrino was coming from. So for the first time ever, not only did we have evidence that there are neutrinos, but there was a direct evidence that they really were coming from the sun. Wow. In fact, Kamiokande and its second generation upgrade, Super Kamiokande, which is even bigger. This is a gigantic, okay? It is many stories told. It's like a 10-story building filled with water, and they have produced image of the sun. The images were beautiful images because you actually seeing the neutrinos that were coming light from the center of the sun. Wow. Then, instead of seeing the sun in light, they were seeing the sun in the neutrino. Wow. So we started to do some astrophysics, but again, they were fewer neutrino events than they had expected, by about factor of 2 or so. So everybody agreed that there was a solar neutrino puzzle. Yes. By the way, this is a little footnote. There was a tragic accident at the Super Kamiokande facility just a year or so ago. I don't know. I've been living in Japan, but I don't know what it is. As they were filling it back up again with water after routine cleanings, one of the photomultiplier tubes improved, and the shock wave traveled through the water, created a chain reaction, and they lost thousands of these photomultiplier tubes. It cost millions of dollars of damage, and so this wonderful detector has been shut down. Ha ha ha, this is how Japanese people are. Ha ha ha. Hopefully it will be rebuilt because it was a great facility doing all sort of good neutrino physics. I don't think it was rebuilt because at that time the politics another political party arose to the as a cabinet to the cabinet, and they decided to cut the fund to the scientific field, especially for such a particle physics. So I don't think so. Well, I will see. I'm gonna check it again. How are we going to understand this puzzle? I think that by the time all of these experiments have been put together and they all agree with one another, no longer will they be dismissed to anyone as being just experimental uncertainty. There are two obvious places where we might not understand the world correctly. Maybe we don't understand the sun, maybe the standard solar model is just wrong, and there are fewer neutrinos produced in the sun than we thought.